So yeah, if you haven't put your Penn State ID into the chat box, please go ahead and do that for me. Thank you so much for that. And we are going to talk about our last lesson before the final here. So this lesson is talking specifically about correlation and then simple linear regression. So it's talking about relationships between different variables. So we have talked about relationships before, but this is going a little more in depth in terms of giving some objective numbers to those and then, what those numbers mean. So for correlation, the different symbols we use for them is a P for population and then R for sample. Don't get this confused with like a P for proportion or anything. That's something often that I feel like people mess up, especially on Wiley Plus. The P looks similar to the one for the proportion. But if I'm correct, it doesn't have the little squiggly on it for this P. It's just a normal P. And then R is the correlation symbol we use for our sample correlation. And you find R with many tab. This isn't something that you can correlate. This isn't something you can equate by yourself. So you would need to use some statistical software for that. And just keep in mind that correlation is unit free, which means that we can have you can use like different values on the X and the Y axis in terms of the unit. So if I were to have a graph here, I could have like centimeters on my x-axis, but I could also have like, inches on my y, and I can still, make a correlation here about, the different points that I had and talk about them because we're looking at, the relationship between these two and, how closely related they are together, so we can still say, that there's a relationship, between inches and centimeters, for example, even though they're not the same scale. So that's something to keep in mind to not let it trip you up in that way. Correlation is always between 0 and 1. Keep that in mind. And technically, so I don't like to say -1 and 1 because then it kind of makes you think about there being like a value to it, but there's not necessarily a value for correlation. It's your strength and your direction. So you're going to have, remember when we did scatter plots, it's very similar. So, we have between 0 and 1, and then based upon the direction of that correlation, so as you can see, the absolute value of R here. So dependent on what number you have, that's going to be the strength of the relationship. And then after you find this, you just decide if it's a positive or negative relationship, and then you kind of just add the positive or the negative in with it. So, you start out with just the positive numbers and then, change it if it does happen to be a negative relationship there. Okay, so once again, as we've been doing, hopefully, you have hypothesis tests as a basis, that this is, also a good review for all the stuff that we've been doing, because hypothesis testing is obviously a unit that we went pretty far into. And, as you can see, it keeps coming up over and over again. So we're going to go through the steps for a hypothesis test for correlation. So remember, our first step is always going to check those assumptions. So in this case, for the assumptions for correlation, we have to make sure that so we call it Pearson's R. That's basically saying, so remember we were talking about, in order to assume that it's normal or whatnot for the other ones, since in this case we're talking about correlation, there's not something necessarily that's like normal. That's why we're talking about in order to use Pearson's R. Then that means that both variables have to be quantitative, so they have to have some sort of number associated, a value associated with them, and also that the relationship between the X and the Y does have to be linear in order for us to do that, because you can't really find a correlation between nonlinear relationships there, because that's not what Pearson's R is based upon. Okay, yeah, so then your null and alternative there, as you can see, and remember this P is specific to correlation. This isn't a proportion P, that's different. So you have your null and alternative there, and so you have, and in this case, you are going to write, that your P is not equal to 0 in the case that, because remember, we can have negative or positive between 0 and 1, so 0 to 1, and then technically 0 to -1. So saying that there is a relationship is basically saying that P is not equal to 0, because if it's 0, that means that there's no relationship, which is what our null is assuming, that there's 0 relationship, so our correlation would be 0. But then our alternative is saying there's some sort of relationship going on, similar to our chi-squared test, where we're trying to see if there's a relationship. And so we have that. And then that's why our alternative is saying that there is a relationship, meaning that it would not be equal to 0. So it could either be greater than or less than 0, but that is showing a relationship. And then test statistic, once again, you are going to have to use Minitab to compute R. That's just, something that you have to use statistical software to find. So on the exams and stuff, I assume you would be, given R to continue with that. To then use it for your third step to determine your p-value, and based upon the test statistic, you get that p-value from the statistical software. And then remember that when you do this, you are going to get that two-tailed test output. So, because like we said, for all alternative hypothesis, it's going to be not equal to. So if you are conducting a one-tailed test, so if in reality it's saying, is there a positive correlation? That's when you're going to change, your alternative to being greater than. So, if your question is going to be, is there a positive correlation? That means that we're going to change our alternative hypothesis is going to be P is greater than 0, because we're talking about it being more than. And then if there's a negative correlation, if that's what your question is asking, I'm writing really small, then our alternative is going to be P is less than 0. So, and I mean, it can also, if it's saying that the correlation is like greater than, 0.2, that can also be a thing. But the main idea here is, one-tailed, or these are going to be your one-tailed tests, and then this is going to be your two-tailed. So yeah, main idea there is when you get the test statistic from Minitab, it's going to automatically give you that of the two-tailed test. So make sure that if you are using one of these, that you do divide whatever p-value you get by 2 in order to get a one-tailed test test p-value then, in order for that to make sense. And then based upon what p-value you get, you're going to choose between the null and alternative. And that's why this step 3 is important, because, if you get a p-value that's a two-tailed test, and, that's going to be double the times of what it should be for a one-tailed test, so you could incorrectly, reject or fail to reject the null based upon that. You'll probably, in that case, you'll probably incorrectly fail to reject the null, because it will be a larger p-value. So that's why, step 3 is important for, it's always important, but just, in this case, for us to make a correct conclusion for 4. And then obviously for 5, you always want to just state that real world conclusion based upon the context of the original problem there. All right. Okay, so simple linear regression, basically, if we break down, the name of it, it's simple because there's only one variable going on, and then it's one explanatory variable, so keep that in mind. And remember, this is going to be quantitative. And then, so that's where the simple regression part comes from. And then linear, all that is saying because it's a straight line. So that's like where the name comes from, per se. And then if we go down here into our the equation for simple linear regression line in a sample, we are going to have our y-intercept as y-hat. So remember, that's going to be whatever value is on your y-axis right here. And then b, and then, sorry, nope, totally incorrect. Yeah. This is it's your y-intercept here. Oop, let me draw this again. Is your b subscript 0. And then your y-hat, this is going to be, like, this is basically what you're trying to find. These are like, if you were to draw like an xy coordinate, that's what these two are showing you here. And so there's that. And then your slope itself is going to be, that's going to be your b1, so that's your slope. And then whatever point, you have, that'll be, oh, I'm not sure what happened there. That'll be your y-hat, and then whatever value that correlates down here will be your x. So pretty self-explanatory. It's just the different parts of an equation there for simple linear regression. So yeah, regression is just using, one or more explanatory variables to predict a response variable. With simple linear regression is just showing that you have only one explanatory variable, which is why we just have one x here. Okay, so these are the assumptions of simple linear regression that we have to, that we make when we first, start working with it. So when we are talking about simple linear regression, these are the 4 different things that we make the assumption that are true basically about them. So first you want to keep in mind that for linearity, and these are things that if you look at the notes, there's more, there's a more detailed, if you go down, you can see like examples of different graphs for each, which it shows like different, like how this is represented graphically, but we'll discuss them more conceptually here. So linearity, basically what you're going to do is use your graph for 2 variables here, your scatter plot for 2 variables, and then basically you're trying to make sure that that relationship is linear, and see, that if you look at the 2 variables and how the dots are lining up, the different points, that's going to show if it's linear or not. Independence of errors, you're going to use your plot of residuals. So this is also going to come out of Minitab there. So you want to make sure that the errors are independent of each other. You don't want there to be some sort of trend, because that's basically saying that the errors are related, which is not what we're looking for. So yeah, independence of errors is just saying that there's not a relationship between the residuals and the y variables. So that means that our y is independent from errors. We don't want it to be dependent on those errors, because that's not what we're looking for. So when you check the residuals, the plot of the residuals versus fits, you want to make sure that, we've been looking for correlations here, but you want this one to be approximately 0, because that's showing that there's not a relationship, and that's what we want. We want the errors to be independent of each other. The third one is normality of error. So basically what you would do here is you're using your normal probability plot, and then seeing if the observations that follow a given line. So you can also look at a normally approximated histogram too. It shows you the same trend there. So basically the main idea here is that you want to make sure that the residuals are approximately normal, to show that, because if you think about it, if the residuals are approximately normal, that means that they're going to create a normal curve. There's going to be a common, residual, and then as it spans out, there's going to be less of the uncommon ones there. So yeah, when you look at the normal probability plot or the normal approximated histogram, you just want to see that the normal probability plot or the histogram, that the observations are near the line there. And then if you're looking at the histogram, it just has to be normally distributed to meet that assumption there. And then for the fourth one, equal variances, you're going to use the plot of residuals versus fits here. And these are all in Minitab that you can see to make sure that you're able to display them and then use them to discuss these assumptions. So this is saying that our variance, so our spread basically for the residuals is the same for all the values of x. So that's saying that the spread for each of the different values of x is the same, because we don't want them to vary, because that's showing that there's not really a relationship. So we're trying to show that there's some sort of relationship there between the explanatory and response variables. So that's where that comes from. So yeah, variance of residuals should be the same across all values of the x-axis. And yeah, you want to make sure, and also for equal variances, you don't want it to show a pattern, because if it shows a pattern, then that's going to show you that there's some sort of like relationship going on in terms of like that the variances aren't equal to each other, because that if there's a pattern, that's not going to show, if they're equal to each other, it's going to show a normal, it's going to show that the residuals are the same, approximately the same across all values of the x-axis. But if it's showing a pattern, that means that they're not going to be the same, obviously. So you can see things like a bow tie, which would be like, basically it's more spread, for these values of the x-axis, but then less for the middle. So that's another assumption that we make there. Okay, so going back to confidence intervals, which was something we talked about, obviously, pretty extensively, but then when we're talking about for a slope, in this case, we do want to keep in mind what we are trying to find out here. So our slope is going to be our point estimate in this case, because if we remember, our confidence interval equation is going to be our point estimate plus or minus our multiplier, times our standard error or our standard deviation. And then also keep in mind that this entire right side of the equation is going to be equal to our margin of error. So this is our general equation for a confidence interval. So in this case, our point estimate is going to be our slope, because we're trying to find the confidence interval for a slope. So we're trying to find, us being a certain percent confident that the slope of our population lies between two variables. So, and then our t value is going to be our multiplier, because we are talking about quantitative variables. So that's when we use our test statistic. And our degrees of freedom for a slope is going to be n-2. So that's something to keep in mind, a little bit different than what we've been using for degrees of freedom. And then as usual, our standard deviation is just going to be our standard error of the slope here. So either be given that or calculate that. All right. Okay, coefficient of determination. This is basically more or less trying to discuss what you found in the end. So the amount of variation in the response variable, that can be explained by the explanatory variable. So whatever you get for your coefficient of determination, it's kind of giving you the percent of the variance in your response variable. So the spread of it, that can be explained by your explanatory variable. So remember, the explanatory variable is our independent variable. So that's explaining our response variable, which is dependent on our explanatory variable. So in that case, for the amount of variation in the response variable, this is what our coefficient of determination is telling us. So if we square r, that's how you're able to find this. And it'll give you a decimal, obviously, which you can transfer to a percent. Make sure you keep in mind the directions. This is why I talked about, you want to use that absolute value of the correlation at first, because in this case, you want to make sure that you do that and then add the negative sign if it is a negative correlation, because obviously if you square a negative number, it's just going to go to a positive number, but it's still, a negative correlation. So you want to make sure that you preserve that by using the absolute value and then adding that negative back in after you go ahead and solve that. So, all right. Okay, and then two last things just to make sure that you think about while we're doing this. Outliers can obviously skew our results, as we've been talking about throughout the entire semester. So in most circumstances, an outlier is going to decrease the value of a coefficient. So if you think of it in this way, so let's say, we had, honestly, like, what if we had a perfect correlation of, let's just say that R is equal to 1. But if you think about it, if we have an outlier down here, this correlation is going to decrease. R is going to end up being, maybe only like 0.95, but it is going to decrease because technically whatever line we had going here is going to need to start, it's going to start trending towards the outlier a little bit. So that's going to start trending this way a little bit. So that you see how there's going to be a greater difference in the residuals here. So our value is going to decrease. So outliers often decrease our R, the value of the correlation. And then also, another way to say this is weakens it, because, R is obviously stronger than our, 1 is obviously stronger than 0.95. And then obviously influential outliers in the data set are going to be the ones that do actually make a change there. And they can they can increase it in that case. It depends, but often, it does decrease in the event of these situations. And extrapolation is something to keep in mind in terms of you want to make sure that you're not using the data that you have to make inferences about things outside of what you your data set. So if I have a data set about the correlation between my exams, or let's say like my grades in my grades in 8th, 9th, 10th, 11th, and 12th grade, and then let's say like my my ice cream intake, because obviously that increases my grades. So we have that there. So we have this, but I cannot extrapolate and say that when I'm in graduate school that if I eat this much ice cream that I'm going to get, that this trend is going to stay like that. So that would be extrapolation, assuming that values outside of your data set, which would be right here, are going to follow that same trend. We can't assume that. So that's what extrapolation is. Basically, you want to make sure that you're only making inferences about the data set that you have and not about those outside of the data set there. All right, let's do some reviews here. So, okay, which of the following cannot be answered from a regression equation? So think about this one, and then we will go over it together. Confidence. Maria, that was like kind of confident. It was like not confident at the beginning, but then it was with the exclamation point. So proud. But so yes, our answer is D. Great job. So when we have our regression equation, we're not able to like figure out if it's linear or nonlinear until we like actually have our data points. Our regression equation is just giving us, what we can use to predict it. So estimate the slope, we can do that because that's just giving us B1. So we're able to do that. But then we have our, if we estimate, instead of that, we're going to have, and then if we predict the value of y at a particular value of x, we're able to do this because, you have your y hat and then equals your slope and then plus your y-intercept and then your slope times your x. So you're able to do A based upon this, because if you're given, let's say you're given that x equals 3 and that, your y-intercept is 4 and then your slope is equal to a half, I can literally just go in here and say, y hat equals 4 plus 1/2 times 3, and then I'm able to predict that y value based upon the x value that I got. So that's why those don't work, and then estimate whether the linear association is positive or negative. We can also do that because you can just look at, your slope and see if it's, plus or minus, and it'll tell you that. So D can't be answered because we don't know that until we actually go through all of that. So great job, everyone, as per usual. All right, let's do this one. So a regression between foot length and height, important, for 33 students resulted in the following regression equation: y equals 10.9 plus 0.23x. One student in the sample was 73 inches tall with a foot length of 29 centimeters. What is the predicted foot length for this student? So try answering this one and then we will solve it together. Yay. Great job, everyone. So where's my annotation? Okay. So what I do for problems like this that are in like paragraph form, I always want to pull out all the important variables that I'm going to use in my equation. So in this case, so we see that, y equals, here's our equation again. So y equals 10.9 plus 0.23 x. So this means that our one student in the sample was 73 inches tall. So that's going to be our x because it says our regression equation between foot length, which is our response variable. So that's y. And then height is our explanatory variable. So that's x. So that means that x is going to be 73 in this case. And then our foot length, y, is, so that's what we're trying to find out. So in this case, so what is the predicted foot length for the student? Since this is like what we have, this is what they actually had was 29, but we're trying to find the predicted foot length, so that's y again. So if we plug this in, we're going to get y equals 10.9. So our intercept plus or minus our slope of 0.23 multiplied by our explanatory variable, 73 inches. And if we do that, we're going to end up getting about 27.69 as our final answer. So this is our predicted foot length of him. So, I mean, this is our actual foot length, so that's going to be y. But in this case, I forgot to put the hats. Y hat is going to be our predicted foot length based upon this x variable here that we have. So our answer is B. So great job. All right. All right, so let's try this one. So in the simple linear regression equation, y equals b subscript 0 plus b subscript 1 times x, the symbol x represents what? So this is just kind of making sure you understand the different parts of an equation here. Great job. Absolutely. So our answer here is going to be D. So if we do recall, so our estimated or predicted response is going to be our Y here. If we do technically predict it, it's going to be Y hat. Estimated intercept is our B subscript 0, and then our slope is our B subscript 1. So that's why these aren't the answers, because we're talking about X, which is representing our explanatory variable. So if we write this out, we are going to have our predicted response equals our intercept, and then plus our slope times our explanatory variable. So our answer is D. Great job. All right. All right, one more, I think. So a study is conducted comparing a student's height versus the height of their father. The correlation between father's heights and students' heights for 79 male students was R equals 0.669. What is the proportion of variation in son's heights explained by the linear relationship with the father's height? So try this one out and we will go over it then. All right, good job. Yep, so our answer is A here. So remember, this has to do with, yes, with our coefficient of determination. So remember, for our coefficient of determination, we're going to square our R value. So in this case, that means we're going to take 0.669 and square it. And that's going to give us about 44.7561. And we're going to, round that to approximately 44 point, and this is for percent, 0.8%. And then since we got that, we're not going to do like plus or minus because all we're talking about is what percent of the proportion can be explained by the linear relationship with the father's height. So remember, it's talking about what proportion of the explanatory variable can be explained by, or what proportion of the response variable, so son's heights. So son's heights is our response. So what proportion of that can be explained by our explanatory variable, which is going to be father's heights. So that's why our answer would be A there. So good job. All right, yay. Great job, everyone, as per usual. Our next group review will be for this chapter again on Sunday, already December, amazing, at 10 o'clock. So stop by if you want more practice for this. We'll start doing some midterm reviews next week. I think I'm doing like one Tuesday and Wednesday night or something. So if you have any other questions for me, let me know. And if not, I'll see you on Sunday or another day, hopefully.